Okay, in the previous lecture we have added this resistance and we have introduced a zero in the system and made the system stable. But when we did the simulation, yes, the PLL is locking, but what we have seen is that because of this resistance, there is a jump in the control voltage. So let's try to analyze this one a little more. Okay, so basically the control voltage is jumping because of the suddenly turning on and off the the current switches. Okay, so this is how it looks like. So it is supposed to be like this, but if the if suddenly a current ip flows through a resistance, so what is going to happen? It's going to happen something like this. So instead of like this smooth, so there will be a jump first of and then it will come down. Okay, so when this ip is turned off, so this is equal to this voltage jump will be ip into rp. Okay, where ip is the current source, where ip is this current source and rp is the resistance. So before it is charging this capacitor which is doing the integration, but then there is a sudden jump, and whenever the switch is off, again the because the IR drop, so there is a IR drop of ip into rp. So whenever switch is on, this voltage difference across this voltage difference of ip into rp appears across this rp, and whenever the current is off, it goes away. Similarly, it happens when this also turns on. So again, the in the reverse way, that jump is going to happen. So let's complete here. So there is a jump, right? So my control voltage will look something like this. Instead of the black color now, it will look something like this. Okay, so we can see that there's a lot of spikes, and the height of these spikes, we know that this is equal to ip into rp. So the only way to reduce these spikes is by adding another capacitor here. So by using another capacitor, it will filter out the spikes. So we are going to add C2 to filter out the spikes. So let me write it down nicely in the new page. So the capacitor C2 is added to filter the noise that arises from IPRP jumping. Okay, so let's draw this one. So this is my PLL model with addition of C2. So this is my PLL model with addition of C2. Okay. So as soon as we add this C2, it's going to add a pole in the transfer function. Okay. So addition of C2 will add a pole in the open loop transfer function. So the addition of C2 will add a pole in the open loop transfer function, and let's see let's see what happens because of that. So to analyze this, we can just make a of course now my filter, it has become something like this. Initially it was only the rp and cp, so but now we have another capacitor c2. Okay, so yeah. So this is my cp. So you can do analyze yourself, and this is my new, the IT is going to flow like this. And if we analyze this one, okay, so easy way to analyze this is, consider it to be 1 by SC2, the impedance, and 1 by SCP, and the whole impedance you can consider it as a Z, and you can do the analysis. So what I mean is, if you see here in this case, the impedance when the RP was in series with 1 by SCP, so the equivalent impedance was, this one. But so just replace this term. Easy way is, just replace this term with RP in series with 1 by SCP, and this whole thing parallel with C2. Okay, so if we just replace this term with this, then we can get the whole transfer function. Okay, so now with this, my open loop transfer function is going to become something like this. It is open. I'm writing it directly. You can try yourself. So, but you are going to get something like this: IP by 2 pi C2 into S plus 1 by RPCP and S into S plus 1 by RP into CP C2 by CP plus C2 into, of course, we have the Kvcio's transfer function, which is Kvcio by S. Okay, yeah. So if I just rewrite it, I can write it as, maybe I'll just combine them. So my HS open is given by, again, IP by 2 pi C2 into C2 into, we can write here Kvco into, of course this is same, S plus 1 by RPCP, and this is S square S plus 1 by RP into, again, CP C2 by CP plus C2. Okay, so if you see here, we have 2 poles at the origin and 1 pole here, okay, at this location, and we have a 0. So if you just write down the location of the poles and zeros, it will be something like this. So my 0 is located at 1 by RPCP. My first pole P1 is located at 0. My second pole P2 is also located at 0. And my third pole is located here, which is 1 by RP into CP C2 by CP plus C2. Okay. Okay, so this is an important parameter that we should remember in terms of solving a type 2 PLL. Okay, so now basically what I'm trying to do is that I'm trying to draw the, the magnitude as well as the phase of this transfer function. Okay, so of course we have first, there will be, as usual, there are 2 poles in the origin. So I have a roll-off of minus, minus 40 dB per decade. Okay, then after this, immediately I have a 0. So 0, and then this is going to like this, and then I'll have another pole. So then this is going to again roll off by minus 40 dB per decade. Okay, Okay, so I have just moved this one a little down. Okay, so let's label it. So this is my minus 40 dB per decade. This is of course minus 20 dB per decade, and again this is rolling off by minus 40 dB per decade. Okay, so now this is the location of my 0 WZ. Okay, and this is the so this is the unity gain frequency. Okay, and this is my W P3. Okay, so this is the omega P3. Okay, so now if you see in terms of the phase, okay, so let's call this to be minus 180, this to be minus 90. Okay, and of course the 0 is here. So let's draw a line, and then this is, and then this is, and this one. If you the phase just it slowly starts increasing because of the 0, and here it will reach minus 135 of course, and then it increases, but then because of another pole, influence of the another pole, it's going to decrease. Okay, and then it's going to again decrease, and of course this point is going to reach minus 135, and eventually it is going to go something like this and go towards the at very high frequency it's going to go to 0. Okay, so yes, so this is the phase margin of this system now. So the phase margin is the point where this I have this gain crossover frequency, or the unity gain frequency. Okay, so this is the phase margin. Okay, so the phase margin, the expression of the phase margin we can write if we know the location of this where it is crossing, like where it is having the unity gain or the gain crossover frequency, and as well as if we know this and this one, right, we can find out the phase margin. So the phase margin can be given by, is approximately given by, okay, so what happens is first this will be influenced, right? So this is the 0 is trying to increase the phase margin, and at this point the contribution that the phase leading at this point will be given by 10 inverse Q by omega Z. So basically it is trying to increase, right? So as we have seen that if my 0 is very small, right, if my 0 is very small and much smaller than this one, then this should go to 90 degree. Okay, provided if the pole P3 is not there. But then if this pole P3 is trying to degrade the phase margin, and it is given by, so it is going to, we can do the subtraction 10 inverse, and how much degradation it is doing at this frequency will be given by omega u, this frequency, by omega P3. Okay, so this is an approximate expression of the phase margin. Of course, the phase margin is further degraded by the delay of the divider. So when we insert a divider, or when this part comes back, there can be a delay. So then this delay we can also incorporate that we'll see later. But this also little bit can degrade the phase margin. Of course, if there is an ideal system, the delay is not there, so then this happens to be the phase margin. But with the addition of the delay, we have to little bit modify this one, or it basically degrades the phase margin a little further. And of course, this point we know that this is minus 135, okay, degree. Okay, so yeah, so with this, this is the complete system of a type 2 PLL. Okay, So basically what we are supposed to do is that with the addition of RP we are adding a 0, okay, but at the same time this is providing a ripple, and with the addition of this C2 it's going to filter up. But then we have to be careful that we cannot make this C2 very large. If we try to make this C2 very large, the system is going to become unstable, okay, because the phase margin is going to reduce as I try to bring this omega p3 closer and closer to this one, okay. So yeah, so this we need to take care while we design the PLL. Okay, till now we have been discussing the PLL where my input frequency is equal to the output frequency. So what if we bring a divider, as we have also discussed before, what if we bring a divider in the feedback part and we get a frequency F out, maybe integer multiplication of the input. So let's see. So we'll discuss about the frequency multiplication now. So till now what we have seen, whether it may be a type 1 or type 2 PLL, we have seen we have the phase detector, we have the phase frequency detector, we have the low pass filter, or I should say that the charge pump, and we have the so better call it as CP or LPF, okay, and we have the VCO, and what we have done is the this is the whole block diagram. We have our omega in or F in and frequency F out, okay, and we have taken a feedback and given to the phase frequency detector, okay. So this is quite analogous in the voltage domain to the op amp, which is where my the negative terminal is connected to the output, and what I'm getting is a simple source follower, okay, a simple voltage follower, okay. So where my, in this case, my V in and V out are same, and this is the case when my V in is equal to V out, almost, of course, if there is no offset. And here also we have, when the phase is locked, we have seen that F out is equal to F in. So now what we want to do is we want to go for a frequency multiplication, okay. So in case of the voltage domain, what we do is that if we want to get a multiplication, right, so we are going to add the division factor here, and that's how we get the voltage multiplication. For example, if I have this is my V in, and we are going to add something like this. So my output voltage is going to get divided by the this simple resistive divider, and will be fed back to this feedback circuit, okay. So if I call this R1 R2, okay, and this is my V out, okay. So if both R1 and R2 are same, we know that the output voltage that we are feeding back here is half, right? So we know that the gain of this one is V out by V in is equal to 1 plus or basically the feedback factor, I should say. So what is the feedback factor here? Feedback factor, the output which is coming back, okay, so the output that is coming back is basically R1 by R2 plus R1. So basically the beta, this is the beta feedback factor, and of course the one gain is inverse of the beta, so which is 1 by beta, and this is equal to R2 plus R1 by R2 plus R2 plus R1 by R1. Okay, so this is 1 by beta, and since the beta is equal to this, okay, so maybe let's write it here. Okay, yeah, so okay, so similarly here also in case of the PLL, if we just if I want my F out to be N times F in, okay, so I want my F out to be N times F in. So here also I need to add a I should add a block which divides my input frequency by a factor of maybe let's N, divide by N, okay. Yeah, so that's how it works, right? So what happens is, like, if this is F out and if I call this a frequency maybe FD, right? So my FD will be equal to F out by N, okay? And here we are trying to make these two frequency the same, or the phases to be the same, and once we make the phase the same, we know that F in and F out will have the same same frequency, okay. And then if FD has the same frequency as F in, automatically my F out will be N times FD, okay. Yeah, okay, so now we have done the analysis for N equal to 1 case, okay. So now how does my analysis change if I go for this kind of characteristics, okay. So this is as if we are telling that if I see from here to here, so it is as if we are telling that I have a VCO, okay, I have a VCO something like this, and if I put a divider, divide by N, right? So if I'm giving some voltage, of course this is V control, okay. If I put a voltage V control, and this is going to give me an omega out, okay. And once we divide it, of course the frequency will be divided by N times, okay. This is a very simple thing. Once we divide the frequency N times, so what we can say is that, right, so basically my new omega out, so since we know that the omega out is equal to omega naught plus k VCO by V cont, okay. So what I'm now doing is I'm dividing everything by N. Omega out by N is equal to omega naught by N plus k VCO N into V cont, okay. So my new omega out, so let's call it the frequency at this point be equal omega prime maybe, okay. So my new omega out, which is coming out of the divider, omega out prime is nothing but the this one, so implies my omega out prime will be equal to omega naught n plus kvco by n into v cont. Okay, so this is a very important expression. So instead of seeing as if I have a VCO and a divider, I can see this whole thing as a new VCO. Okay, so this whole thing as if it is a new VCO. Okay, and which has a characteristics of this one. Okay, so where it is something like this. I have a new VCO. So I have a it is having as if I have a new VCO here. Okay, VCO dash, where I have my same P cont, and this is the omega out dash. Okay, and and this is the characteristics of this new VCO. So the V cont and omega out dash, and it has the y-intercept at omega naught by n, and the slope of this line is this one. Okay, so k VCO by n. So only thing which changes, of course, when we are doing the analysis, this value doesn't comes. Okay, basically we are doing the small signal analysis. So only the thing which comes in the analysis is k VCO by n. So whatever that we have analyzed remains the same, except we should just replace the k VCO with k VCO by n. Okay, when we are doing the when we are introducing this divider. Okay, so so for this case, especially for a type 2 PLL with a divider n, the transfer function is going to look something like this. So the type 2 PLL with charge pump, okay, having divider n, okay, at the feedback part. Okay, so it will now be, so what does open loop means? So when we are opening the loop, right, so what is the total loop gain? Sometimes we also call it loop gain. So if I'm providing a signal here and then here, so when we see the complete transfer function, so basically starting from here to here, so that means because my now divider is coming in the part, so the KVCO will be divided by n. Okay, so now my transfer function will be 2 pi C2 KVCO by n. All the things remains the same. So S plus 1 by RPCP S square S plus 1 by RP into C2 CP by C2 plus CP. Okay, so this is the transfer function of the open loop gain, and this we need to analyze to find out the phase margin. So if you observe here, the only difference between the open loop case without a divider and this case is just that the n is added here. Okay, so basically what it means is that the whole graph is going to shift by n times as I include the divider in the part. So basically what is happening is going to happen that, see, the whole graph is going to shift down. So if you see, because of the shifting, the UZB is going to shift towards this one, and there's a possibility that the phase margin can reduce because of this. So that's why we need to analyze it properly, and generally this is compensated. If we see the equation again, it is compensated by increasing the IP. Okay, so this is the open loop case. Okay, and to find out a closed loop response, HS closed, right? So the closed loop response, we know that it is in voltage, in a simple feedback circuit, we know that it is A 1 plus beta into A. Okay. So now whatever we have calculated this open loop gain, it is nothing but this beta into A. Okay. So from this, if I want to get the A, I just need to divide by beta. Okay. So yeah, so what it means is that in this case what I will have here is, we just need to uh, so in the 1 plus beta into A, which is basically the HS open only. Okay, open loop gain, and here I just need to multiply this one with the 1 by beta. So since beta is 1 by n, so 1 by beta is n, so into HS open. Okay, so this is the this is the closed loop response. Okay, sometimes we will write this HS open also as the loop gain, as we can also express something like this loop gain, but it's fine, both are fine. Okay, yeah. So with this, we'll end the discussion here. In the next lecture, we'll use some parameter, practical values of this RP, C2CP, IP, KVCO, and we'll try to solve problems and also do some simulation with practical values of these parameters. Thank you.